All right, so the first chapter is really an introductory chapter, it's just to get you a feel for this course. Okay. The problems are easy and so on. But anyway, so we'll introduce you to units that we use in physics. Okay. Now, before I get into this, let me motivate the subject. Okay. I'll tell you what the subject is about. Okay. So you guys have all seen an air hockey table. Okay. So let's say a puck is sitting on the table. It's floating on a cushion of air. What's the cushion of air doing? What's it about? Yep. Yeah, so reduces friction tremendously. Okay. So if the puck is sitting on the table, it won't move. What would you have to get it to move? You push it. Yeah. Okay. You push it and it'll start accelerating. And if you let go, what will happen? It'll keep going and its velocity will not change. Okay? So that's an observation you make. You observe things in nature, and if it happens all the time and everywhere, then you state it as a law. Okay, so here, so we just discovered the first law of motion. Okay, so that's the first law of motion. That's called the Newton's first law of motion. Okay. Mr. Galileo was the one who actually discovered it. Okay. But I'll tell you in a second why we call it the first law of motion. Why we call it Newton's first law of motion. Okay. Then, so if no force acts on the object, then the object will maintain a constant velocity. Okay? So then the next natural question is, what do you have to do to change its velocity? Yeah, apply a force on it. Okay, and that's what Newton discovered. Okay, so Mr. Newton's found out that if you apply a force on it, this is how its velocity will change. Acceleration is the rate of change of velocity. And now you can see that this guy, see, if force is zero, this equation tells you if the force is zero, acceleration is zero, and velocity is constant. Okay? So really the first law is a special case of the second law. Okay. So you see, physics, we notice things in nature, and then we state laws. And we state laws in the form of a mathematical equation. Because this is the most succinct way to say a lot of things. Okay? So physics is about discovering laws that govern nature, and all these laws are stated as mathematical equations. Okay? What does physics apply to? Like we said, everything. How many different phenomena occur in nature? Countless. Infinitely many. You think that laws to describe all these phenomena will be infinite in number. But really, there's only very few physics laws that govern all the behavior of nature. In fact, at the fundamental level, there's only 4 laws. There's only 4 different kinds of forces. Everything in nature, in principle, could be explained using these 4 laws. Okay? So that's what physics is about. So for instance, so by the way, velocity, and again, I'm saying stuff that we'll give details to. We'll elaborate on these things. Velocity is a vector. What is a vector? I'm sorry?
It's pointing in the direction.
Yeah, so it has magnitude and direction. So for the velocity, the magnitude would be its speed, and direction would be, the direction it's moving in.
It's never going to be negative.
I'm sorry?
It's never going to be negative. It's the magnitude.
The magnitude is not going to be negative. Yep. All right, so I'll give you one more example. So, again, you observe phenomena happening in nature, and then you codify it as a law. Okay, an explanation that explains that behavior. You codify it as a law. So, for instance, we've been studying celestial objects for a long time, okay? And we observed planets. I'll keep it simple. I won't be precise, okay? So I'm just trying to give you a feel for it, okay? So for instance, the Earth goes around the sun at 30 kilometers per second, okay? Its speed is constant, okay? Is the velocity of Earth constant? Yes, no, I got both answers.
Well, its speed is constant, but it's always changing direction.
So the question is the velocity constant? No. Okay. So you just learned that acceleration is change in velocity. Acceleration tells you how fast the velocity is changing. Okay, so you observed this in nature. I gave you the numbers from Earth, but we didn't observe Earth. We observed other planets. But anyway, Earth is going around. Its velocity is not constant. It is accelerating. So you just made that conclusion. So there must be a force acting on it. What's the force acting on this object then? I'm sorry? That's the force of gravity. And Mr. Newton discovered this force of gravity. Okay? So again, the point is you observe phenomena in nature, and then you try and come up with a law that explains it. And once you come up with a law that applies to a certain phenomenon, you will, it becomes a law only when it applies to it. No phenomena can break that. Now, of course, we have a hierarchy of laws. So, for instance, these are all classical laws. They're approximate laws. They apply to large objects and so on. Okay? Does this apply to electrons? No, it doesn't apply to electrons. Okay? So we have many approximate laws. So for instance, all the gas laws and stuff like that, they apply to classical systems like this. Okay? The ideal gas law doesn't apply to a cloud of electrons, for instance. Okay? So the more precise laws are quantum mechanical. But if you want to kill a fly, you don't want to use a hammer. Okay? So we don't want to use a hammer to kill. So you don't want to use quantum mechanics to describe the motion of your car. Okay? Newton's laws, they're a good enough law to describe the motion of your car. Okay? So that's what we'll be doing classical laws. All right, so now that I've motivated it, motivated physics, Let's get into the slides. So the laws of physics describe the behavior of everything from galaxies to atoms. Okay? Except that when you're trying to describe atoms, you want quantum mechanics. And when you're trying to describe the behavior of galaxies, classical laws are good enough. Okay? So it describes all of nature. Yeah. So the laws of physics are surprisingly few, even though you describe an infinite number of different phenomena, okay? Implying a simplicity to nature's apparent complexity. Okay? All right, so here's some pictures just to bring home that point. Laws of physics apply to all different scales. So these are pictures of atoms. Everybody know what an atom is? So I'll just draw a simple little atom. Let's say lithium. I'll draw lithium-3. Okay. Lithium-3 is the second element on the first column. Okay. What does the 3 mean? I'm sorry? It tells you the number of protons and the number of electrons as a consequence. Okay, so it has 3 protons, and so the red number, it's the mass number, okay, and that's close to, is that 7, okay, so it's got various isotopes, and the 7, close to 7 tells you the most common isotope is 4 neutrons, okay. And these are energy levels. These are pictorial representation of the energy levels the electrons can occupy. This innermost level can only occupy 2 electrons. Yeah. So, okay, you fill that with 2 electrons. And here is the 3rd electron. So this is the ground state of the lithium atom. Okay. Of course, in the ground state, all these levels are not occupied. And how many of those levels are there? I'm sorry? There's an infinite number of levels. You want to excite this lithium atom. Here's an excited lithium atom. Okay. This atom doesn't like to stay in its excited state too long. Let's say generally if the transition is allowed within a billionth of a second, this guy will fall down, and what will he do? He'll emit a photon. Okay. All right, now in physics we're interested in numbers and stuff like that. The size of the nucleus is about 10 to the minus 15 meters. The size of the atom is 10 to the minus 10 meters. Okay, all the mass of the atom is essentially there. That red number is right there. These guys, the protons and the neutrons, are 2,000 times heavier than the electron. So the electrons weigh almost nothing. Okay? So all the mass of the atom is right there. And look at that, that's 100,000 times smaller than that. All of chemistry happens only with the electrons, and that too only with these outermost electrons. So in all of chemistry, you don't even touch these guys. Okay. So for instance, all those guys in column 1, they have 1 outermost electrons, and in all their life, all they're trying to do is get rid of this guy. So that guy, lithium, you see fluorine, on the other hand, has 7 electrons here, and an 8 electrons in the outermost shell would make it a stable configuration. So you see lithium is happy to give one of its electrons to the last but one column of elements. Yes, sir. All right, anyway, so here's an atom. The size of the nucleus is 10 to the minus 15 meters. The size of an atom is 10 to the minus 10 meters. Okay, a good picture to have is if an atom was as big as a football stadium, the nucleus would be the size of a marble. Okay. All right, so let's get to this picture. Okay, so each of those dots is an atom. Okay. That's about 10 to the minus 10 meters. Okay, so here's 10 to the minus 10 meters. These guys are phytoplankton. Okay, these guys are the first guys in front trapping solar energy for us. Okay, so they convert solar energy into chemical energy. Okay, and these guys are from the sizes from 1 micrometer to a millimeter. Okay. So these guys are 10 to the minus 6 meters to 10 to the minus 3 meters. That's the size range. Yeah. Again, this is just giving you a scenic view of things. You don't have to remember any of this stuff. It's just to get under your skin, that's all. Okay. Here's pictures of a couple of galaxies. Two colliding galaxies are located 300 million light years from Earth in the constellation. Okay? Eventually, these galaxies will merge into one. Okay, so we live in a Milky Way galaxy. A Milky Way galaxy is the Milky Way galaxy is about 100 million light years across, 100,000 light years across. So you see a light year is 10 to the power of 16 meters. 100,000, that's 10 to the 5. So this galaxy, the size of the galaxy is about 10 to the 21 meters. So the point of this picture is the following. See, here are these objects of very different sizes. This guy is 10 to the power of 31 times bigger than this guy. 10 to the power of 31 is a million, trillion times, 10 million, trillion times larger. But the physics laws apply to everything. Okay. All right, I'll tell you one more interesting thing about this. This picture is taken using a scanning tunneling microscope. You guys know what that is? Anybody have heard of a scanning tunneling microscope? Okay, so here's how this thing works. So let's say you want to take a picture of this surface. Okay, it's got to be a metallic surface. So let's say you want to take a picture of this surface. Okay, so what you do is you have an electrode like this, and you will scan the surface with the electrode. Okay. So now I'm going to draw surface like this. So now let's say this surface has bumps like that. So the atoms have bumps. All right, so what we're going to do is, again, I'm just giving you rough numbers. We'll connect 25,000 volts or something like that. Okay. And then we'll scan this electrode at a constant distance. So the electrode is at constant height. When you have a bump in the surface, what will happen is electrons will jump across to the electrode. When the gap is small, more electrons will jump, and the current is high. When the electrode is near there, when the gap is low, when the gap is great, the current number of electrons jumping is small. Did you guys understand that? Okay. Smaller the gap, more electrons tunnel across the gap. So that's where so scanning comes from the fact that you're scanning the electrode. Tunneling comes from how many electrons are tunneling. And the word microscope comes from? I'm sorry? You're using microscopes to look at tiny objects. Okay? All right, so what that picture is that picture is a proxy for the current. What you're measuring is really current. And then you're generating an image. Okay. A bright spot. What is a bright spot? High current. What is a dark spot? Low current. Okay. So that's how you're creating an image. Okay. All right. So physics is you're codifying observations in laws. Okay, so when you're making observations, you got to make measurements, and so you have to have a system of units to quantify your measurements. Okay, and so we want to use a set of units that's universal. You don't want your friend in China using a different set of units than you. So everybody agrees to use a common set of units, and these are called the SI units, the System International Set of Units. And it turns out that this is an amazing fact. Every quantity that you can measure physically is made up of one of these basic 7 quantities. Anything you can think of. Okay. Energy, momentum, force, current, pressure, everything that you can think of is made up of one of these guys. Okay? And in fact, the stuff that we'll study in Physics 1, everything that you study, force, pressure, energy, all those guys are made of only these 3 quantities. So every house we build in the first semester is made of these 3 bricks. Okay. We'll talk about the Kelvin in Physics 2, mole, and so on. Okay. And so meter is a unit for length. Okay. Kilogram is a unit for mass, and second is a unit for time. Okay. So, and then you agree to. Okay, so so you arbitrarily pick a stick, okay, and everybody agrees that we'll call this a meter. Okay. You could have started off with this big a stick and called it a meter. It doesn't matter. Okay. As long as everybody agrees what a meter is. Okay, so this is a meter. Can you hold up your water bottle? Okay, that much water is about a kg. Yeah. A second so you guys know how we start off defining time, right? So here's how we start off defining time. There's the sun. We'll call it noon. That's 24 hours. And then you divide that into smaller and smaller periods and you get a second. 24 hours is, that's 24 hours. 1 hour is 3,600 seconds, so you have a second. Now that's how we started it, but then we eventually had to refine all these definitions. Why did you have to refine all these definitions? Yeah?
A lot of those things aren't constant, like the length of the day is constant.
Oh, very good. Okay, so why is the length of the day not constant? I'm sorry?
Slow it down.
I'm sorry?